Hello everyone, this is Asra Sultana, Assistant Professor in Triple Department, ISL Engineering College. I am taking the subject Power System Operation and Control for final year Triple students. Today's class, I am going to discuss about steady state analysis of load frequency control of an isolated power system. So before actually seeing that, let us do a quick revision of what we have studied in previous classes. So we have seen about the necessity of why to maintain frequency as constant, and we have seen the load frequency and excitation voltage regulator of turbo generator, and we have seen the single area case of load frequency control. So continuation of this load frequency control of single area case is the steady state analysis, then will be the dynamic response. So let us once again see the complete block diagram representation of load frequency control of an isolated power system we have seen in previous class. So load frequency control of a single area system. So let us consider the problem of controlling the power output of generators of a closely knit area so as to maintain the scheduled frequency. So why we have to maintain the frequency as constant? So change in frequency may cause change in speed of the consumer's plant, so which may affect the production process. And also we have to maintain the frequency constant so that the power stations run satisfactorily in parallel, and the various motors which are operating on the system will run at desired speed, and correct time is obtained from the synchronous clocks in the system, and also the other devices can function properly. So that's why you have to maintain the scheduled frequency or to maintain the constant frequency. So we are considering a problem of controlling the output power of generators in a closely knit area. So this area is called as coherent group. So inside this group, all the generators will speed up and slow down together, maintaining the relative power angles. So such an area is called as control area. So boundaries of control area will generally coincide with that of individual electricity board company. So to understand the load frequency control of single area system, let us consider a single turbo generator system supplying an isolated load. So this is a schematic diagram of a governing system of a steam turbine. So there are four main components of this system. That is, first one is speed governor. So or more specifically we can call it as a fly ball speed governor. Second one is hydraulic amplifier. So this is a speed control mechanism. Then is linkage mechanism. So this entire A, B, C, C, D, E, this is called as linkage mechanism. And next is speed changer. This is the speed changer. Okay. So the turbine speed governing system has four main parts. That is speed governor, hydraulic amplifier, linkage mechanism, and speed changer. So what is the operation of a speed governor? This is the heart of the system which will sense the change in speed, and hence it will sense the change in frequency. So when the speed increases, fly balls will move outwards and the point B on the linkage mechanism will move downwards. And so as speed increases, the fly will move outwards and the point B will come downwards. And if the speed decreases, then this point B will move upwards. Okay. Next is hydraulic amplifier. Hydraulic amplifier comprises a pilot valve and main piston arrangement. Okay. So this is pilot valve and this is main piston. Low power level pilot valve movement will be converted into high power level piston valve movement. So this is necessary to open or close the steam valve against high pressure steam. Linkage mechanism. ABC is a rigid link pivoted at B. So CD is another rigid link pivoted at D. This link mechanism will provide movement to control valve in proportion to change in speed. So whenever there is changes in speed, this will linkage mechanism will show its movement. It will also provide the feedback from the steam valve movement. So if there is a changes in the steam valve, then also it will show the changes. The linkage mechanism will show the changes. Okay. Then is speed changer. Speed changer will provide steady state power output setting for the turbine. So it's whenever it is moving downwards, upper pilot valve will be opened. Okay. So more speed, why it is getting open, so that more steam will go into the turbine under steady conditions. So with this we will get more steady power output. And reverse will happen with the upward movement of the speed changer. So with lower movement is more steam will get inside. Upward movement less steam will get inside. Okay. Next is model of speed governing system. So under steady state conditions, let us consider that the linkage mechanism is stationary and pilot valve is closed. So steam valve is opened by some definite magnitude and turbine is running at constant speed with the turbine power output balancing the generator load. Okay, this is the initially we are assuming here that the system is running with the steady conditions. Linkage mechanism is stationary, that is there is no movement in linkage mechanism. This is stationary and pilot valve is closed. Pilot valve is closed and steam valve is opened by some definite magnitude. Okay, and the turbine is running with some constant speed and some output is it is showing. Okay, with some load. Now let us consider that F naught is the system frequency. F naught is system frequency. PG naught is the generator output. That is generator output is the input output of the turbine, and YE0 is steam valve setting. So we are considering here the linear incremental model around these operating conditions. Let the point A on linkage mechanism, see here this point A, be moved downwards by a small amount delta by A. Okay, we are considering here that point A is moving downwards by an amount delta by A. So it is a command which will cause the turbine power output to change, and therefore delta by A can be written as Kc delta Pc. So this delta Pc is nothing but here commanded increase in power. Delta Pc is commanded increase in power, and the command signal delta Pc sets into motion a sequence of events. Okay, because of this movement of point A moving downwards, so it will set into motion a sequence of events, that is pilot valve will move upwards. So high pressure oil flows on top of the main piston moving it downwards, and steam valve will open, turbine generator speed will increase, that is the frequency will increase. Let the two events mathematically we can write them as, that is delta by A contributes to L2 by L1 delta by A or minus K1 delta by A, that is upward of minus K1 Kc delta Pc, and increasing frequency delta F causes the fly balls to move outwards, so that B will move downwards by amount K2 dash delta F. So moment of C with A remaining fixed at delta by A will be L1 plus L2 by L1 into K2 dash delta F, that is equal to K2 delta F, that is downwards. So net moment of C will be equal to delta Yc equal to minus K1 Kc delta Pc. This plus K2 delta F. So similarly now moment of D, that is delta Yd, is amount by which pilot valve will open. It will be contributed by delta Yc and delta Ye, and can be written as delta Yd is L4 by L3 plus L4 delta Yc, and this one will be L3 by L3 plus L4 delta Ye. So moment of delta Yd depends on its sign opens one of the ports of pilot valve, admitting high pressure oil into the cylinder. So thereby it will move the main piston and opens the steam valve by delta YE. So we are making certain assumptions here. So first one is inertial reaction forces of main piston and steam valve are negligible. Second one is because of first case, rate of oil admitted to the cylinder is proportional to port opening delta YD. So volume of oil admitted to the cylinder is proportional to time integral of delta YD, and delta Y movement is obtained by dividing the oil volume by area of cross section of piston. So delta YE we are writing as K5 integral 0 to T minus delta YD dt. So from schematic diagram, what we can see that positive movement of delta YD will cause negative movement of delta YE. So negative sign will be used in this equation here. So now taking the Laplace transform of these three equations. So delta YC, delta YC, delta YD and delta YE. So for these three equations, we are taking the Laplace transform. So I am going to get as delta YC of S is minus K1 Kc delta PC of S plus K2 delta of S. Delta YD is K3 delta Y3 YC of S plus K4 delta YE of S, and delta YE of S is minus K5 1 by S delta YD of S. So eliminating delta YC of S and delta YD of S, we can write delta YE of S as minus delta PC of S minus 1 by R delta F of S into KSG by 1 plus TSG into S. Now what is this R here? R is K1 Kc by K2, that is speed regulation of governor. KSG is K1 K3 Kc by K4, that is gain of speed governor. TSG is time constant of speed governor, that is 1 by K4 K5. Now these equations I am representing in the form of block diagram. So we are writing the transfer function, that is KSG by 1 plus TSG into S here. Then taking a summing point, we have to get the equation as delta Y of S is delta PC of S minus 1 by R delta of S into KSG by 1 plus TSG into S. So delta PC of S minus, because here it is plus and here it is minus. Okay. So delta PC of S minus 1 by R into delta F of S, okay, multiplied by this entire value, that is KSG by 1 plus TSG into S, is equal to delta Y of S. So this is the block diagram representation of a speed governor system. Now let us see the turbine model. So the first model is the governor model is completed. Now we have to see the turbine model. Next we have to see the generator model. So turbine model. So we can relate the dynamic response of steam turbine in terms of changes in power output to changes in steam valve opening delta YE. So figure A is showing the two-stage steam turbine with a reheat unit. So dynamic response is influenced by two factors. One is entering steam between inlet valve and first stage of turbine, and second one is storage action in the reheater, which will cause the output of low pressure stage to lag behind that of high pressure stage. So turbine transfer function is characterized by two time constants. For ease of analysis, it will be assumed here that turbine can be modeled to have a single equivalent time constant. So we are considering here only a single equivalent time constant, that is transfer function of this is given by kt by 1 plus tt into s. And input of this will be delta ye fs, and output of this will be delta pt of s. Now let us consider the generator model. So increment in power input to the generator load system is given as delta pg minus delta pd. Delta pg is delta pd, that is incremental turbine power output, and what is delta pd? Delta pd is the load increment. So this increment in power input to system is accounted in two ways, that is first one is rate of increase of stored kinetic energy in generator rotor. At some scheduled frequency f0, the kinetic energy is given as Wke not equal to h into PR kilowatt. where PR is the kilowatt rating of turbo generator and H is defined as the inertia constant. So kinetic energy is proportional to the square of the frequency, and kinetic energy at a frequency of F naught plus delta F can be given as WK is equal to WK naught into F naught plus delta F by F naught whole square, or approximately it is equal to HPR into 1 plus 2 delta F by F naught. So rate of change of kinetic energy can be written as d by dt of W kinetic energy is equal to 2 HPR by F naught d by dt of delta F. So increment in power inflow to system. First way is the rate of change increase of stored kinetic energy. Second one is the as frequency changes, motor load changes, and as motor load changes, speed also changes, and rate of change of load with respect to frequency, that is rate of PD by dou f into delta f can be written as B delta f. So that is dou PD by dou f can be regarded as nearly constant for small changes in frequency delta f. So we can write this as dou PD by dou f into delta f is B delta f. So what is B here? B can be determined empirically and it is positive for predominantly motor load. So we are writing the power balance equation delta Pg minus delta Pd is equal to 2 HPR by F naught d by dt F delta F plus B delta F. So dividing through all this equation by PR, we are going to get delta Pg per unit minus delta Pd per unit equal to 2H F naught, 2H by F naught divided dt delta F plus Bp per unit delta F. So like taking the Laplace transform, we are going to get the value of delta F of S as delta Pg of S minus delta Pd of S by B plus 2H by F naught S. So this can be written as delta Pg of S minus delta Pd of S into Kps by 1 plus Tps into S. So what is TPS here? 2H by F naught, that is power system time constant, and KPS is equal to 1 by B, that is power system gain. So this equation can be written in the form of block diagram. So what is the equation? Delta Pg of S minus delta Pd of S, that is here Pg of S minus Pd of S multiplied by KPS by 1 plus TPS into S equal to how much? Equal to delta F of S. Okay. Okay, this equation delta Pg of S minus delta Pd of S multiplied by Kps by 1 plus Tps into S, okay, equal to delta F of S. Pg of S minus Pd of S multiplied by Kp of S by 1 plus Kps by 1 plus Tps equal to delta F of S. Now we got the block diagram representation for governor model, turbine model, and generator load model. So combining all three to get the complete block diagram representation of a load frequency control of single area system of an isolated power system. Okay. So in the first diagram we have seen that. So let us see the first diagram. So this was our first diagram. Speed governor system, that is delta Pc of S is the input, Ksg by 1 plus Tsg into S, delta Y of S. Here negative sign here we are having for 1 by R into delta F of S. Then second one was delta Y of S is the output, here it is input, and then transfer function is Kt by 1 plus Tts, then delta Pt of S is output. Next third diagram what we have seen, continuation here. So delta Pg of S minus delta Pd of S into Kps by 1 plus Tps S is equal to delta F of S. So all three we have combined here, okay, combined here, and feedback also we have got here. So this is a complete block diagram of a single area system of an isolated power system. So let us see the steady state analysis. So there are two important incremental inputs to the load frequency control of a single area system. First one is delta Pc and delta Pd. Second one is delta Pd. What is delta Pc? Delta Pc is nothing but change in speed changer setting. Delta Pd is the change in load demand. Let us consider a simple situation in which the speed changer has a fixed setting, that is delta Pc is 0 and load demand is changing. So we are considering a case where speed changer is fixed and load demand is changing. So this is known as free governor operation. So for such an operation, steady change in system frequency for a sudden change in load demand by an amount delta Pd can be written as delta F of S at delta Pc of S equal to 0. Here we are taking into consideration as delta Pc is equal to 0. So delta F of S at delta Pc of S equal to 0 equal to minus Kps by 1 plus Tps S plus KSG KT KP KP KSG KT KPS by R by 1 plus TSGS into 1 plus TTS into P delta PD by S. Okay. Now we have to take the steady state condition, that is delta F at steady state delta PC equal to 0 equal to S into delta F of S at S tends to 0 equal to, so S tends to 0 we have to write here, that is KPS by, how much we are getting, KPS by 1 plus KSG KT KPS by 1 R into delta PD. Gain KT is fixed for turbine and KPS is fixed for power system KSG. So speed governor gain is adjustable by changing lengths of various links. So let us assume here that KSG is adjusted such that KSG into KT is nearly equal to 1. So KPS equal to 1 by B and B equal to dou PD by dou F by PR, that is in per unit megawatt per unit change in frequency. So delta F can be written as minus of 1 by B plus 1 by R into delta PD. So this is the steady state load frequency characteristics of a speed governor system. So this equation, that is delta F is equal to minus 1 by B plus 1 by R into delta PD, gives the steady state changes in frequency caused by changes in load demand. Speed regulation R will be adjusted so that the changes in frequency is small, that is it can be order of 5% from no load to full load. So linear incremental relation can be applied from no load to full load. So this is the figure showing the linear relationship between frequency and load for free governor operation. So what is the free governor operation? That speed changer is fixed and load demand is changing. So for this we are seeing the uh, steady state characteristics, and it is showing the linear relationship between the frequency and load. So for y-axis we are taking frequency, x-axis we are taking the load. Speed changer is said to give a certain scheduled frequency at 100% of full load. And the droop or slope of this relationship is minus b by minus of 1 by b plus 1 by r, that is equal to minus r. So the slope of this curve is minus r. Okay. Power system parameter b is generally much smaller than 1 by r. So that's why we can neglect the b, and delta f can be written as minus r into delta pd. So earlier our equation was like this, that is my delta f is equal to minus of 1 by b plus 1 by r into delta pd. So we are neglecting here this entire term, we are taking as how much? Minus r. Okay. So typical value of B can be 0.01 per unit and 1 by R can be 1 by 3. So B is neglected in comparison. So we are taking into consideration only minus of 1 by 1 by R. So it will become how much? Minus R delta PD. So delta F is equal to minus R delta PD. So the group of the load frequency curve is maintained, mainly determined by R and the speed governor regulation. So increasing load demand, that is delta PD, is met under steady condition partly by increased generation, that is delta PG, due to opening of steam valve, and partly by decreased load demand, that is due to drop in the system frequency. So KSG into KT nearly equal to 1. So delta PG I am writing as minus 1 by R delta F, that is equal to 1 by PR plus 1 delta PD. Decreasing system load is B delta F, that is BR by BR plus 1 delta PD. So contribution of decreasing system load is much less than the increasing generation. For typical values of B and R, delta PC can be written as 0.971 delta PD, that is decreasing system load is 0.029 delta PD. So let us consider the steady effect of changing speed governor setting, that is delta PC of S is delta PC by S. So with load demand remaining fixed, that is delta PD equal to 0, steady state change in frequency we can obtain as delta f of s at delta PD of s equal to KSG KT KPS by 1 plus TSGS 1 plus TTS into 1 plus TPS plus KSG KT KPS by R into delta PC of PC by S, or delta F at steady state condition we are getting as KSG KT KPS by 1 plus KSG KT KPS by R into delta PC. KSG into KT is nearly equal to 1 and delta F is equal to 1 by B plus 1 by R into delta PC. So if the speed changer setting is changed by delta PC, so and load demand is changing by delta PD, steady frequency change is obtained by superposition, that is delta F is equal to 1 by B plus 1 by R into delta PC minus delta PD. Uh, According to this equation, frequency change caused by load demand can be compensated by changing the setting of the speed changer, that is delta PC is equal to delta PD for delta F equal to 0. And from this figure, load to load frequency plots we can get, that is one to give scheduled frequency at 100% rated load and other to give the same frequency at 60% rated load. Okay, so first one is showing at 100% rated load, second line is showing the 60% load. So speed changer we are getting at two different loads, 100% load and 60% of load. So this is a steady state analysis of a single area case. Thank you students. Hope you understood today's class. So next class I will tell about dynamic response and proportional plus integral control and load frequency control and economic dispatch control. Then last topic can be two area load frequency control and pool operation. So you may expect a question of short question, that is what is control area in today's class and how the frequency, already I said this also earlier class, how why the frequency remains constant, what is control area concept, and draw the block diagram of single area. You may get a question of draw the block diagram model of a load frequency control for a single area case, or you may expect a question of the explanation of load frequency and excitation voltage regulator of turbo generator. Okay, so these are today's class. I hope everyone understood. Thank you students for watching the video.